Okay, let's start.
We're going to do physics today. So we're going to do work, one small application of physics. So we're going back with the work and section 5.4. Not sure right than we got it last time. But some basic definitions. One, work is sort of the activity of a force, is sort of a measure of energy transfer, and we measure it at force times distance. And by the way, this is the distance. So this is usually talking about force on, you're thinking of it as acting on some object, on an object. And if you can measure the distance, the object moves in the direction of the force. You call that the work done by the force. And that's the basic definition, but things aren't always that straightforward. This guy's great if your force is constant and distance easily measured. Right. There's another idea of work, and this one is far more general, where we think of work, W here means work, as the integral of the force function dx from A to B. It's the work done object by A. It's possibly variable, so here you can actually treat your force as a function. Work done on an object by a possibly variable force in moving from position A to B. The catch here, the distance here is measured along the straight line. To generalize this idea of work for a path that's not exactly shooting in a straight line, you need like multivariable calculus. You need some vector calculus in that. You need what's called the line integral, and we only know about regular integrals. But that's sort of the essential idea. We're very rarely going to be using this because things are never going to be that easy. Of course, it's a Calculus 2 class, so we're mostly going to be relying on this. But this definition includes this definition, it turns out. If your force is constant, then, 2 includes 1. If your f of x, which is your force, is, say, k, a constant, then you would get work would be the integral from a to b of the constant dx, which is just going to be the constant times b minus a, which that ends up being the force, and that ends up being the distance. So this is the far more general interpretation of work, and so we'll use this pretty much all the time. Yeah.
Sorry, what again does distance measured along a straight refer to?
Hmm?
When you said the catch is
Yeah, in general, work is force times distance.
Mhm.
Now, distance is just how far you've traveled,
Mhm.
but there are a bunch of ways you can travel from point A to point B. You can travel along a curve, you can travel along a straight line, you can travel over a hump, things
Oh.
like that.
So it has to be linear?
Yeah, so for our purposes, it has to be linear motion. Like there's a force that hits an object and it moves it in a straight line.
Okay.
And then with that interpretation, we can use a regular integral to use it.
Okay.
If you want to vary the path, so this is good for if the force can vary. If you want to vary the path, you need something called a line integral, which you need like Calc 3. They'll do that after Calc 3. So yeah, so that's the basic idea. So we're going to go over some. So to really treat this topic in its full generality, you will need some multivariable calculus, but we're going to keep things simple. We'll look at a few applications. The first one we're going to look at is Hooke's law. So this one is talking about the force exerted by a spring. We're also going to look at pulling problems. So for example, if you have a mass at the end of the pulley and you're pulling it up, how much work are you doing by pulling it up in a straight line? We're also going to look at pumping problems. Which is kind of like if you have a container and you have some sort of liquid in that container, could be water, could be something else. How much work will it take to pump the liquid out of that container? So these are the three basic ideas we're going to be looking at, and we're going to be using this conceptualization of work to solving these problems. And so the idea is always you're going to go back to these two ideas, but the setup for these three situations are going to be somewhat different, and you kind of have to be a little bit creative how you're setting them up. Once I show you, it's going to be a strategy that you can apply. Also, there are a few comments on units in this class. When you see the word pounds, or LB is the shorthand for it, this is a unit of force in the empirical system, it's kind of complicated. There are so many variations on this unit, it's not even funny. There's pounds and pounds force and pound mass, but we're going to keep it simple. Whenever you see pounds, you can think of that as a unit of force. Whenever you see kilograms, that's an SI unit, or kg. That is a unit of mass. Right? So when we say force here, we mean weight, like how much you weigh. So that's a measure of how gravity is pulling on a body, right? So it's not really a measure of how much stuff it takes up, whereas mass is the amount of matter in the object. Right, so these are very different. We also know by Newton's, so usually keep empirical units and SI units together, i.e. if force is measured in, say, pounds, then you'll usually want to use like feet for distance. Right, so you're going to want to keep things, like if you're using empirical units, use it with everything. Use it with distance, so you're going to use like feet, maybe inches, but you want to keep these guys together. If you're talking about kilograms, of course you're going to want to convert to meters. distance will tend to be measured in meters. What else do I want to tell you about the units? So the first thing is you should recognize that pounds is a unit of force, kilograms is a unit of mass. Keep your units together. Another thing is there's one of Newton's laws that says we can think of force as mass times acceleration. Is that the first law or is it
Second.
the second law? The first one is the equal and opposite reaction one,
Yeah.
and the third one is like inertia. Okay, so that's force equals mass times acceleration, which sort of means, notice that in work, what we're integrating is force, which means if you're given mass, so if you're given something in kilograms, you should understand that is mass, it's not a force. So in order to put it in a work integral, you need to convert it to a force. And how you do that is using this law. And so you would just take whatever kilograms you're given and you'd multiply it by the acceleration, which will usually be due to gravity. So we can use this to convert from mass to force. Right, so here this is force, this is mass, this is acceleration. If A is gravity, we may call it G. And we have G, there are two basic units that you might want to have it measured in. It's 9.81 something, but we'll take it as 9.8 meters per second squared. So that's if you're using the SI units and your distance is in meters, your gravity will be 9.8. So if you're given something in kilograms and you want to convert it to force, you have to multiply it by 9.8, is the basic idea. You can also, if it's somehow needed in the empirical sense, which it usually won't because this will already be a force, it's going to be 32 feet per second squared. So these are just some known quantities at this point. And so, for units of work, here's the idea. If we know that if using kg and meters, the units here will be what's called the Newton meter. Right? This is also called the joule. The Newton is pretty much the scientific standard unit of force. It's called a Newton. Okay. And so that's the force needed to actually move a mass of 1 kilogram by 1 meter per second. If using pounds and feet, and the units of work is, it's called the foot pound, foot dash pound. And this is all some commentary. I think in the handout I spoke a little bit about this and the importance of knowing your units. One thing that you really want to know about your units is that a lot of times a work problem would be described to you as a word problem, and so when you're reading the word problem, the units that you're seeing in the problem can indicate to you what kind of quantity you're looking at. And so that's why it's kind of important to know how the units work. Right? So you'll know that, oh, he told me 5 pounds, that's him telling me the force. Or he said, you know, you should know what the units represent. Okay. So let's deal with the first application. Let's do some work. So we're going to do Hooke's law. I'll get down to what the law really states is that the force to stretch or compress a spring by a length x is proportional to the distance it is being stretched. The constant of proportionality in this case for a given spring is called its spring constant. So this will vary by the spring, what it's made of, how strong it is, how thick it is. There will be some sort of constant. You realize that the longer you're stretching the spring, the more force you'd have to apply to stretch it even further. And the force you're stretching it by will be proportional to how far you've already stretched it. Turns out that's true for a spring. As long as you don't stretch it till it's deformed and it can't recoil and go back on itself, right? The amount of force you're exerting to stretch it will always raise by a linear amount, i.e. F is equal to kx, is what Hooke's law tells us. This is the force needed to stretch, compress the spring by distance x. And k is called the spring constant. And this varies with the spring. X is the distance stretched or compressed. So to compute the work done, to compute so again, work, because we know it's the integral of force, it's going to be the integral of kx from A to B. Okay. Because this guy here, according to Hooke's law, this is how we measure force. So whenever you're doing a spring, you happen to be talking about a spring, stretching or compressing a spring, you want to find out how much work are you doing in doing this. This is the integral you're going to set up. It's going to be kx. This is the work done. Constructing a spring from A units beyond its natural length and that phrase beyond its natural length is important, to B units beyond its natural length. So if the spring is just there and is just by itself, you don't have to exert any work. The work really starts coming once you stretch it beyond its natural length. So if you have here, this is a spring length L, then you can talk about stretching it from, say, this length to that length, and how much work would you have taken to do that? Then this distance here will be your A, and that distance here will be your B. So you can talk about, oh, there's a spring that's 5 inches long. How much work is done in stretching it from 7 inches to 9 inches? Okay, then you wouldn't use 7 and 9 in your integral, you would use 7 minus 5 and 9 minus 5. So you'll go from 2 to 4. Okay, so that's important. The limits that are on your integral are distances away from beyond its natural length. So work, how you can think of it is the starting point beyond its natural length. And the ending point beyond natural length. Of k times x dx. Now there's a lot of explanation that went into that, but these are the easiest problems, the easiest word problems to actually do. Once you actually get the idea in your head, it's easy to apply, right? So Hooke's law states this: the force needed to stretch or compress a spring is proportional to the distance you've already stretched it, and this constant of proportionality, it varies by spring. It's called the spring constant. And so because we know that work is the integral of force, to find the work done in stretching a spring from A to B is given by this integral. And where your A and B are dependent on the natural length of the spring. So let's actually do an example to make sure we kind of get what we're talking about here. So this is example 1 from handout. I kind of explained all that. Okay, so problem 1, a spring has length 15 inches. Okay. A force of 750 pounds is needed to compress it to 12 inches. Find the work needed to compress it an additional 3 inches. And I gave you the answer there, it's in inch pounds, so I didn't convert to feet or anything. So we know that L, the natural length, is 15. So how would you use Hooke's law to figure out what the force is? Well, we know, well, the idea, you don't need to figure out the force, you kind of need to figure out the K here. So by Hooke's law, and I'm writing extra here, but we know that F is equal to Kx. This means that 750, that's how much force they told us is used, 750 pounds is needed to compress it by a length of, compress it to 12 inches, right? So what is the length that we've compressed it? 3. That gives you the spring constant for this particular spring, 750 over 3, which is what, 250? So this is the spring constant for this spring. this means that the work for this spring is going to be the integral of 250x dx, where now you can plug in the limits to figure out what lengths you want to stretch it between. So you basically use Hooke's law to find the constant, the spring constant, and then we can integrate that. Okay, so how do we start? So we know we're integrating 250x, that's true. What's the original?
Original length?
No, the limits.
No,
Make sure we can read the limits here. How far beyond its natural length are we starting?
8.
So it's important that you're not starting from starting from the spring not being stretched. It's already compressed a little bit. It's already compressed by 3 units beyond its natural length, and we want to compress it further by 3 more units. So what's the last limit?
6.
So that would be your integral. So this is 3 units beyond natural length. And we're going up to 6 units beyond natural length. We already compressed it by 3 units, now we want to compress it by 6 units, and we're going to find the integral. And so that one's not so bad, that's 250x squared over 2 between 3 and 6, it's going to be 250 times 6 squared over 2 minus 250 times 3 squared over 2, and...
4,500.
Huh?
4,500 minus 1125.
Yeah, I think I wrote the answer here. It's 3375, I think. Yeah.
So we can't use this formula to just like calculate the force to stretch it beyond its natural length a certain distance? Like it has to be the force to go.
Well, the formula for that is going to be Hooke's law. But here we're computing the work done. So it's not like we're computing a force here, we're computing the work. So this is in inch counts.
We also could use that to compute the work to stretch it like just beyond its natural length.
Yeah, so you can, if you want to start from your natural length and stretch it, you can just start here at 0
Okay.
and then go to where.
Okay.
So that's kind of basically it with Hooke's law. You use Hooke's law to figure out the k. Plug in the k, it's always going to be this easy integral for a spring, and you just have to read carefully to make sure you're choosing the right a's and b's, because they might not be the numbers that are expressly said to you. You have to think of them in terms of how far from the natural length are we, and that's your start and your end.
So this is compressing, and if we stretched it, would it be the same answer?
Yeah, the stretch and compress in
Okay,
the
so
magnitude.
There's
it's
no
gonna be
like
the same.
sign, okay, gotcha.
Yeah, you don't have to worry about the sign. And you might be worried about what if we're like a stretching and a compressing is happening in the same problem. Well, one, I'd never actually give you that, and two, the answer is you'd always ignore half the problem and use the positive limits anyway. Because if you're going, say, from a compressed state to a stretched state, you don't actually have to apply any work for it to go back to its natural length. You really start applying the force, because if you release the compression, it will just bounce back to its natural length, and you use the force to stretch it further. So you'd only care about the stretch part of that. Whereas if you're going from a stretched state to a compressed state, again, the part from the stretched to the natural length, you don't apply any force to get it there, it does it on its own, and then you press it more. So you only ever care about from the natural length, whether you're going left or right, you think of it as a positive distance because you can always ignore the other one. But that's never a situation I'd ever ask you anyway, but just in case you're curious. Let's talk about lifting and pumping problems, right? So we want to know how much energy we'll need to lift something, or how much work it's going to cause us. You can do this idea. And again, this is more like lifting in a straight line, but it's a standard kind of problem. Lifting / pulling problems. The idea here, we're going to use the Riemann sums idea. So basically we find the work to move each infinitesimal piece. Then sum all these with an integral. Okay, so we're going to sort of use the Riemann sums approach to these kinds of problems. So this would be something like, well, I'm going to give you an example. I'll just jump right into it and sort of show you how you might do this. Let's look at example 2. We have a 100-foot cable that weighs 300 pounds. It hangs off the top of a tall building. Find the work needed to lift the cable to the top of the building. So, this is not as easy as a force times distance kind of thing, right? It's not like you take up a 10-pound weight and you put it on a table. Right here you're pulling up the rope. Now, when you pulled up some of the rope, the remainder of the rope that's hanging off has less weight, right? So you're varying the force with which you're pulling, right? So when the entire rope is dangling off, you need a lot of force to start pulling it up. But when half the rope has already been pulled up, you'll need half your strength to pull it up. So the force you're exerting on the rope as you're pulling up is changing. It's actually decreasing a little bit. Okay? So we have a variable force here. So the more of the rope you've pulled up, the less work you have to do to pull up the remaining of it. So what is the total work needed to pull up the thing? So the idea is, so here we have our building, and here's the 100-foot cable hanging off of it. The idea is behind this sort of principle is what we're going to do is we can think of moving this rope up in terms of sections. So you can pick like one section of this rope, right? Which you can call its length. Some people use delta y, but let's say it's delta x. Right? So there's a length of this rope, and you, for a minute you're just going to focus on moving that one piece. Because that one piece is sort of like just lifting something up and putting it on the table. We just have to figure out the force times distance for that one piece. And then we'll do that for all the little pieces along the rope. So I'm now going to be focused on one little section of this rope that has 100 feet. So the total length is 100 feet. So here's how we're going to go about it. For one, especially since the idea is to set up a Riemann sum, we're going to set up like some sort of coordinate system. I like to put the origin at the bottom. I know some people put it at the top, but the idea is going to be the same no matter what. So I say the bottom of the rope, I'm going to call this position x equals 0. And I will call position x to be the position of the thing, the section that I care about. So this is distance x to get to that infinitesimal slice that I care about. So now I want to figure out what is the work needed to move that little piece to the top of the building. In other words, what is the distance that I have to move that thing?
100 minus x.
100 minus x is going to be the distance I have to move that piece. So if I think of the bottom of the rope as marking some point in space where that's 0, this piece I care about moving is at height x, then the distance I have to move it is 100 minus x, and that is important because work is the force times the distance we're moving it. Okay? And so now, if I think about the work for this one little slice of the rope per cable, I'm going to look at it as the force times the distance to move that one little piece. Okay? So let's start by setting that up. What is the force to move that one little piece? Well, I know I have a 100-foot cable. It weighs 300 pounds. So a length of delta x will weigh Can you figure that out? How can you figure out the weight of some length of the cable? How much does each foot weigh? You start by the units, right? We have 100 foot, and it always 300 pounds, so how much does each foot weigh? It was 300. Right, each foot of this cable weighs 3 pounds, right? 1 foot of this cable is going to weigh 3 pounds. So how much does delta x feet of this cable weigh?
Delta x times
3. Right, 3 times delta x. Since the rope or cable weighs 3 pounds per foot, delta x feet weigh delta x times 3 pounds per foot, right? Because we have delta x feet. So the feet cancel, and so we get 3 delta x. So this is our force, 3 delta x. Well, that's not the total answer. So that's one part of the equation that we have. We see that the distance is 100 minus x. This means that your work is going to be 3 delta x times 100 minus x, or 3 times 100 minus x times delta x, just to be very suggestive. And this is just for the one slice. Now if you look at the total, we're going to add up all these slices, add up all these things with delta x's. So we kind of think of this as a Riemann sum. There's an infinite number of sections, and so my delta x is the length of each section. That becomes your dx when you throw it into an integral. So this is from A to B. Now, with this setup, you can kind of figure out the work needed to move any length of the cable, right? So your limits are really going to talk about what lengths of the cable you want to actually move. It turns out that in the question we want to actually move the entire cable, right? So we're lifting, what is the set of x values that we're lifting here? It's going to be all x values from 0 all the way up to 100. That will lift the entire cable, right? They could ask the question, oh, what is to lift the top half of the cable or whatever, right? And you would change the limits accordingly. So your limits here kind of describe the length of the thing you want to move. And so here, total work will be the integral from 0 to 100 of 3 times 100 minus x. X. I think I actually calculated that, so this is 1,500 foot-pounds by I mean, compared to the integrals that we've been doing and the ones you'll see on the test tomorrow, I would assume you can get through that integral. It's just a polynomial. Yeah. So that's the work. The other questions are kind of variations on this. I mean, those will go through quickly, but we're kind of out of time. But this is an important idea. Hooke's law and this guy. So whenever you're talking about a pulling problem, you want to be pulling something up, which the length of the thing decreases as you're pulling, so the force will change. This is sort of the way we do it. We basically cut it up into a bunch of little pieces of length delta x and figure out what is the work to move that one thing, and integration comes into add them all up. So we figure out the force times distance for one of them and add it up with an integral. And you can even think of this as the force that you're applying to that thing, is the integral force. Stop there and pick up well, tomorrow after the test.
Yeah.
Oh, the time.